Hello, everyone. When talking about the process of kidney function and talking about the process of glomerular filtration, you have to also include a discussion of the pressures that lead to filtration, right? So just like when we talk about kind of general circulation, systemic circulation, and we got to the level of the capillaries, we talked about capillary filtration. That's essentially what we're talking about here because if you recall, the glomerulus itself, the glomerulus is a capillary bed. Okay, it's a slightly different capillary bed in that it receives blood from an arteriole and it also leaves from an arteriole, but it's still a capillary bed, right? So there's still going to be pressures that are acting on this capillary bed that are either going to promote filtration or oppose filtration, right? So we'll talk about three different types of pressures, and then we'll put those three pressures together for one pressure called the net filtration pressure, right? So one pressure that we'll look at is referred to as a hydrostatic pressure, right? So hydrostatic pressure, if you look at the term hydrostatic, hydro is referring to water, is referring to the liquid, and then static is referring to the kind of the stasis of that liquid. So that pressure that is being exerted by that liquid just by the weight of that liquid. So by the water or of the blood or something like that. All right. Now, when we talk about hydrostatic pressure, it is forcing fluid and it is forcing solutes out of a solution. Okay. So if there is a blood hydrostatic pressure, it is forcing things out of that blood. All right. So this first one here, glomerular blood hydrostatic pressure, this is the pressure of the blood within the glomerulus, right? So this is essentially blood pressure, okay? The blood pressure that is within the glomerulus, right? Which is the capillary bed, right? So this is forcing things out, right? And so we've discussed before that filtration is the process of moving things from the blood. We're moving it out of the blood, and we're ultimately moving it into the capsular space, and then ultimately into the renal tubules, right? And so if glomerular blood hydrostatic pressure is forcing things out here, so you can see in this orange arrow here, 55 millimeters of mercury, that's forcing things out of the blood. So this is promoting filtration, right? The second one is called capsular hydrostatic pressure, right? So you can think of this one as being the same thing as glomerular blood hydrostatic pressure, except that it's promoting fluid going back into the blood. All right. So in other words, it's the pressure of the fluid within the capsule. So within Bowman's capsule here, this glomerular capsule, the pressure of the fluid in that space pushing back into the blood, right? So in this case, because we're going back into the blood, this is opposing filtration, right? So glomerular blood hydrostatic pressure and capsular hydrostatic pressure, those are both going against each other, right? Those are opposing each other, right? And then the last one we'll discuss here is blood colloid osmotic pressure, right? So if you recall, whenever we did systemic blood vessels and talked about capillary filtration, we talked about how the presence of proteins, the presence of those large proteins in the blood act to exert an osmotic gradient and hold onto fluid in the vessel, right? And so in our glomerulus here, we're having the same thing occur. And so we have these proteins that are in the blood. Normally, the majority of our proteins are not filtered. They're too large to pass through the filtration membrane that we've discussed previously. And so if they don't pass through the filtration membrane, then they stay in the blood. And if they stay in the blood, they exert an osmotic gradient to retain water in the blood, right? And so in this case, because we're trying to keep things in the blood and with this type of pressure, this is opposing filtration, all right? So you have glomerular blood hydrostatic pressure, capsular hydrostatic pressure, and blood colloid osmotic pressure, right? So you can put all three of these together. So you add the two together that are opposing filtration. So capillary hydrostatic pressure here, right? So you're adding this one plus blood colloid osmotic pressure because those two are both opposing filtration. And then you take your blood hydrostatic pressure and you then take that minus the sum of these two, so your capillary hydrostatic pressure and your blood colloid osmotic pressure, and you get some number, right? And so if we kind of add these numbers here, so our net filtration pressure, and for this net filtration pressure, keep in mind, if you are to get filtration, So if you are actually going to have filtration occur at the level of the glomerulus, this pressure has to be positive, right? The net filtration pressure has to be positive, right? So you take your blood hydrostatic pressure, right, which we said was 55, minus the sum of capillary hydrostatic and blood colloid osmotic pressure. So we'll take these two, 30 and 15, that's 45, so we take 55 minus 45, and so we get a net filtration pressure of somewhere around positive 10. We have a net filtration that is positive, so if we have a positive NFP, we're going to get filtration, right? Now, we didn't mention one pressure that you may be looking at here, right? So we mentioned blood hydrostatic pressure, we mentioned capsular hydrostatic pressure, we mentioned blood osmotic pressure. What about the capsular osmotic pressure, right? So the osmotic pressure exerted by the proteins in the capsule. Well, if you recall, we said that proteins under normal circumstances don't get filtered into the capsular space, right? Or if they do, very, very few, very, very small proteins. So the amount of protein in the capsule, in this capsular space and in this capsular fluid, is negligible in terms of the amount of protein, or there's none there at all, right? And so if it's negligible or there's no protein there at all, those proteins can't exert any osmotic force or exert an osmotic gradient because they're not there, right? And so essentially, your capsular osmotic pressure is essentially zero, right? Because under normal conditions, there aren't any proteins in that capsular fluid, and so you don't even include it here, right? So it's essentially zero, or if it's anything, it's extremely small, and it's essentially negligible, right? So if you're curious as to why that pressure was not there, that's the reason. It's because we, under normal conditions, don't filter out those proteins, okay? So we can look at this, and this filtration, we can then look at it over a span of time, over a period of time, and get something known as the GFR, the glomerular filtration rate, which we've alluded to. So this is the total amount of filtrate, so the total volume of the things that we have filtered out by all the glomeruli in the kidney. So you have somewhere around 1 million nephrons in each kidney, and each nephron is composed of a glomerulus, so you have somewhere around 2 million, maybe slightly more. So it's the amount of filtrate formed by all these glomeruli, all these nephrons, in the kidney for each minute, right? And so for our GFR, we'll look at, we'll typically express it in milliliters per minute, right? So what is the flow rate here and the production of urine as it flows through the kidney in terms of milliliters per minute, right? And so if you have differences in your net filtration pressure, right? So if you have differences in this information that we just talked about here, the more you filter, the more you're going to be circulating urine through the kidney and producing urine, right? So you'll have a higher glomerular filtration rate if you have a greater net filtration pressure, right? So you can do different things, and you can alter the glomeruli, and by altering the glomeruli, you can alter how much is filtered, and then you can alter your glomerular filtration rate, right? So if you're going to decrease your GFR, you can do a couple of things, right? So here, if we look at this top one, if we look at our afferent arteriole, remember the afferent arteriole is bringing blood into the glomerulus. The blood then circulates through the glomerular capillaries. It then leaves via the efferent arteriole, right? Well, if we decrease the size of this vessel, right, so we constrict the size of the afferent arteriole, decreasing its lumen, decreasing its diameter, this is going to result in less blood flow coming into the glomerulus, these glomerular capillaries. If there's less blood in here, there's going to be a lower blood hydrostatic pressure. And if we look back here, the lower this blood hydrostatic pressure is, the lower our filtration rate, or the lower our filtration pressure. And we said that if you have a lower net filtration pressure, you'll have a lower GFR, right? And so we'll end up decreasing our GFR right here, okay? Now, you can also increase the rate of blood flow out of the glomerulus, right? So this is essentially resulting in the same thing, but via a different mechanism, right? So instead of having less blood come in, we're allowing more blood to leave more quickly, right? So normally, in kind of a steady glomerulus has a normal GFR, the afferent arterial is larger than the efferent, and this allows more blood to come in, less blood to flow out, and this maintains our GFR. But in this case, so maybe we have some circumstance going on in which we need to lower our glomerular filtration rate. We can increase the size of this efferent arterial, right? Now, you can also do the opposite things, right? So you can increase your GFR. So if you look at this top one, this is kind of the one that we just described. And if you look at both of these here, in both, you have the afferent arterial, on both of these images, be larger than that of the efferent arterial. So this allows a lot of blood to flow in to the afferent arterial, into the glomerulus, but the rate of flow out of the glomerulus is much lower, right? It's much slower and lower because the size of this vessel, this efferent arterial, is much smaller, right? So if you have a lot coming in via one size vessel and so much going out by a smaller vessel, it's going to build up in this glomerulus, build up in this in these glomerular capillaries, and that's going to result in an increase in net filtration pressure, right? Because the blood hydrostatic pressure is going to go up. You increase the blood hydrostatic pressure, you increase the net filtration pressure, and if you increase the net filtration pressure, you'll increase the GFR, so you'll have an increase in urine production, right? So maybe you have lots of blood, a higher systemic blood pressure, you have lots of blood flowing to the glomerulus, and something like this occurs. Now we'll talk about here in a little bit, here in a second, how the kidney largely maintains the same glomerular filtration rate even with changes in blood pressure, systemic blood pressure, that causes it to increase and causes it to decrease. So changes in systemic blood pressure usually don't have a large influence on or a large effect on the glomerular filtration rate. Okay. So here you can see these. You can see these same things. So you have afferent arterial coming in, right? You can see it's much larger than the efferent. So you have so much blood coming in, right? This contributes to the blood hydrostatic pressure, right? And this is out, so you know that this is the capillary or glomerular blood hydrostatic pressure. You have the capsular hydrostatic pressure here, opposing filtration, right? So the pressure of the fluid in this space. And then you also have the osmotic pressure exerted by the proteins in the blood. And this is also opposing filtration, right? So you can do 60 minus the sum of 32 plus 18. So 32 plus 18 is 50. You do 60 minus 50, you get somewhere around positive 10 net filtration pressure. Again, we're positive, and so we'll have a net movement of things out of the glomerulus into the capsular space, and then from the capsular space into the renal tubules, right? Now, recall from previous discussions that not everything that will ultimately be eliminated in the urine is filtered out at this point, right? You have something known as tubular secretion, in which you have things that are still in the blood, right? So you may have things come in here through the afferent arterial, circulate through the glomerulus, leave via the efferent arterial, and then at another point when these vessels kind of come near the tubules, things will then be secreted from the blood into the tubule, and then it will be lost, right? So not everything that's lost or put into the urine and excreted in the urine is initially filtered here. A lot of it is, but some things are later secreted from the blood into the renal tubules, right? So to maintain our GFR, so to maintain this glomerular filtration rate, we have a couple of mechanisms that allow this to occur, right? One of these is called the myogenic mechanism. One of these is called the tubuloglomerular feedback mechanism, right? So we'll talk about the myogenic, and then we'll talk about the tubuloglomerular, all right? So for our myogenic, the term myo is referring to muscle, right? And so what's happening here is this is referring to the change or the response of the smooth muscle in the afferent arterial in response to changes in blood pressure, all right? So we've discussed before in previous lectures that as you alter the blood pressure, the smooth muscle in that tunica media of vessels is going to reflexively contract, right? And so as you have an increase in blood pressure, okay, I guess we'll start with the decrease here, okay, since this is the first one. So imagine you have less pressure in your systemic circulation, right? So you have a lower blood pressure. Because you have a lower blood pressure, you're going to have less distension or less pressure on the afferent arteriole, all right? So this results in dilation, so the vessel becomes larger. If the vessel becomes larger, that allows more blood to flow into the glomerulus, right? Because the blood vessel is bigger, right? And so what we're looking at here is we're looking at this kind of left image right here, right? So this middle one would be normal, kind of normal blood pressure. This here on the left, this is a decrease in blood pressure. So you see that we have this large increase in the size of the afferent arteriole, so that's what we said here, dilation, which leads to increased blood flow. So you have lots of blood coming in, okay? If you have lots of blood coming in, you're then able to kind of make up for the decrease in systemic blood pressure that would have resulted in less blood coming in, right? And so you get this reflex, this autonomic response that allows you to maintain your glomerular filtration, right? So the net result in both of these is maintaining your GFR, okay? So you have more blood coming in, you have a greater blood hydrostatic pressure, results in a greater net filtration pressure, you have more filtration, okay? You have a greater GFR. Now, you could do the same thing if you had increased blood pressure, right? So instead of having a decrease, now we're over here to the right, you have an increase in blood pressure. Well, if you have an increase in blood pressure, naturally you're going to get more blood flow to the kidney, which would increase GFR. So to maintain it at where we previously were, you do everything the exact opposite of what we just discussed, right? So in this case, now you have constriction of the afferent arteriole. So as a lot of blood is coming in, you have a reflexive contraction of the smooth muscle in the afferent arteriole. This decreases the size of the afferent arteriole. If you decrease the size of the vessel, obviously there's going to be less blood that's able to enter the glomerulus. This kind of drops it drops the net filtration. It drops the blood hydrostatic pressure, which drops the net filtration pressure, and helps to maintain that GFR in response to this increased systemic blood pressure, right? So all this is saying is that in response to a really high blood pressure, systemic blood pressure, and in response to a very, very low systemic blood pressure, you're still able to maintain more or less the same glomerular filtration rate, the same GFR, and you do so by altering the size of this afferent arteriole, which alters the amount of blood, which alters the blood hydrostatic pressure, net filtration pressure, and ultimately the GFR, okay? Now, the second mechanism is referred to as the tubuloglomerular feedback mechanism. So if you look at and you think of the term tubuloglomerular, what we're looking at is we're looking at the response of the renal tubules and how it can exert an effect on the glomerulus or the effect on the glomerular filtration rate, right? So what this is looking at is this is essentially what you can think of as a backup mechanism to the mechanism that we just described. So it's kind of a backup to the myogenic response, right? So what this is doing is this is detecting not necessarily changes in pressure, but what it's doing is it's looking at and detecting changes in the composition of tubular fluid in response to pressure, right? So initially, if we have an increase in blood pressure, right? So the previous mechanism we talked about was trying to maintain the GFR in response to changes in blood pressure. But initially, a change in blood pressure is going to result in kind of an immediate and quick increase in GFR. If you have an increase in GFR, this is going to result in more filtration. And so if you have more filtration, then you're going to have more things in the fluid, right? More things in that tubular fluid that are then going to be passing through the renal tubules, right? Some of those things are sodium and chloride, right? So if you have an increase in your sodium and chloride content, so if you look over here at number 2, you have an increased delivery of sodium and chloride, right? This sodium and chloride in the renal tubules will work its way through the proximal tubule, through the descending limb of the loop of Henle, through the ascending limb, and it will ultimately pass into the distal convoluted tubule, right? Now, we've mentioned before that the distal convoluted tubule has something known as the macula densa cells, right? The macula densa cells are part of the juxtaglomerular apparatus, which is responding to changes in blood pressure and changes in the composition of the tubular fluid, right? So what these can do is this macula densa, these are these set of cells here that are very tightly packed together, right? So macula densa is referring to these packed cells that are very dense and very close together, right? You can see them easily on a histological image as well. So it's these images, or it's these cells right here. These are essentially chemoreceptors. They're sensors that are detecting the changes in the composition of the tubular fluid as it passes by. And so as it passes by, they can result in the release of different types of vasoactive substances, so substances that are going to result in a change in the size of the afferent arteriole, so of the arterioles leading into the glomerulus. And what you can do is if you have increased sodium and chloride here, this means that you had increased filtration, and you had increased filtration because you had an increase in blood flow into the glomerulus, right? So that was the issue. So to correct that, you do something to decrease the amount of blood flow into the glomerulus, and you do that by vasoconstricting the afferent arteriole, right? So if you come over here, you say, number 4, you increase the resistance of the afferent arteriole. If you do that, you result in a decrease in renal blood flow, so the amount of blood flow coming into the kidney or into the glomerulus. And if you have an increase, or if you have a decrease in blood flow, you have a decrease in blood hydrostatic pressure, you have a decrease in net filtration pressure, and if you have a decrease in net filtration pressure, you'll have a decrease in GFR, right? So both of these mechanisms, myogenic and tubuloglomerular feedback, are both resulting in a maintenance of GFR and kind of maintaining GFR in some homeostatic range, okay? Now, you can also alter your GFR through different types of stimulation, right? So one of these is sympathetic stimulation, right? So you're physically exerting yourself, exercise, some type of fight or flight, sympathetic response, something like that. The end result is going to be a decrease in GFR because that situation is serving to increase the GFR, right? So we're trying to maintain homeostasis here, right? So what you can have happen are some of these cells of this juxtaglomerular apparatus called granular cells. So if we go back here, you have these granular cells here of the juxtaglomerular apparatus that can sense changes in pressure. All right, and so what you have in this case, you have them release renin. Okay, you release renin, and we'll talk about renin here in just a second. All right, but the ultimate result is what of what we're trying to get to is to have a decrease in the amount of blood flow coming into the kidney. If you have a decreased amount of blood flow into the kidney and into the glomerulus, you have decreased pressure, and if you have that, you'll have decreased filtration, right, or decreased glomerular filtration rate, right? So we'll come back to this renin. There's a whole system called the renin-angiotensin-aldosterone system that we'll look at in just a little bit, all right? Now, you can also have a change in GFR by altering the release of something called atrial natriuretic peptide, and we've mentioned this previously before as well. So this ANP, atrial natriuretic peptide, the term natri here, N-A-T-R-I, this is referring to sodium, right? Atrial is referring to the atria of the heart, right? So in response to increased stretching of the heart, right, increased distension of the heart, this increased stretching of the heart reflects an increased amount of blood, right, an increased amount of blood flow in the heart. And so if you have this increased amount of blood, you're going to have this stretching, you're going to release this ANP. And this ANP is going to do a couple of things, right? One, you're going to have a inhibition of the release of that renin that we mentioned in the previous slide, okay? If you have a decrease in the amount of renin release, you're going to get all these downstream effects that result in an increase in the amount of blood flow that can enter the glomerulus. If you have an increased blood flow in the glomerulus, you get more filtration, you get more GFR, and so you get more blood ultimately leaving, because the liquid here in the blood is water and it's getting filtered out, and so you lose more in the urine, so you're increasing the GFR, and that's serving to correct our initial stimulus, which was a lot of stretch of the heart as a result of an increased amount of blood, right? So we had lots of stretch in the heart due to the blood, and now we're going to decrease blood volume and blood pressure as a result of increasing our our glomerular filtration, right? And it's all because of this atrial natriuretic peptide right here, okay? So we've mentioned something else known as aldosterone. You can essentially think of ANP, this atrial natriuretic peptide, having the opposite effect of aldosterone. These two are antagonists to each other, right? ANP results in more fluid being filtered, more fluid being lost in the urine, more sodium excretion. Aldosterone is doing the opposite. It's promoting sodium reabsorption, thus promoting water reabsorption and adding to the volume of the blood. All right. So this is the system that I've just mentioned. We'll go over it more in just a little bit in a separate part. But what it's essentially doing here is this renin here. You can see renin right here from the juxtaglomerular apparatus. It's stimulating the conversion of some of these different protein molecules that ultimately leads to things that cause an increase in blood pressure, right? So you get increase in sympathetic activity, you get an increased amount of reabsorption of sodium and water, you get aldosterone secretion, you get constriction of blood vessels, so you get an increase in pressure, you get an increase in the amount of ADH secretion, so you're reabsorbing more water, so the more water is coming back into the blood. You can also stimulate thirst centers in the hypothalamus, so you become more thirsty, so you drink more water, which increases blood pressure. You have all these downstream effects that all result in an increase in the amount of water coming back into the blood, which increases blood pressure. And you do some of those things by altering the physiology of the kidney, right? So you're altering the amount of sodium and water reabsorption through aldosterone. You can also alter it through anti-diuretic hormone secretion as well, right? So we'll stop here with this part, and we'll pick up in the next part, and we'll talk about something known as renal clearance and how this relates to GFR.